Hello, my friends. Today we are going to continue with the topic DC motors. In the last lectures, we have already derived a formula for the armature's voltage. In this formula, EA, which stands for the armature voltage, is given by Zp divided by 60A times phi n. Z here means the number of conductors. A is the number of the parallel paths. So if your motor is wave wide, then A is equal to 2. And A will be equal to P for lap winding. So it depends on how your armature was wound. And as I said, right, P is the number of poles, right? I've already said it here. And phi is the magnetic flux per pole. Each pole will be associated with a magnetic field, which is proportional to the field current. N is the rotational speed in RPM. So in this case, you have a formula like this. And now I'm going to change the formula. Instead of expressing the armature voltage in terms of rotational speed n, right? So can we convert this n into omega? I think the answer is pretty simple. So what you need to do is 60, move the 60 here now, 60A, right? And then 2 pi, and then you have put phi here, and then 2 pi n, right? The expression will multiply by n at the top and by 2 pi on the top and 2 pi at the bottom. So in this case, what you are going to end up with is a chunk of constant, right? And then 2 pi a, and then here you have a number of rotations, revolution expressed in 2 pi n divided by 60. So this is equivalent to omega. So this is the formula we need to pay attention to. And it's not difficult to memorize it. So now, in this lecture, we are going to elaborate more, and we are going to learn the characteristic of shunt-connected motor. Shunt means parallel. So I'm going to erase the definition because we are running out of space. So in this case, you have this formula, and Z is the number of conductors, which is not going to change, same as P. The number of poles is fixed. 2 pi, right, it is the constant. A is the number of parallel paths, which depends on the winding topology. During the operation of the motor, this parameter is not going to change. So the only thing that can change during the operation of the motor is the phi here. The phi is related to the polar flux, the magnetic flux per pole, and this magnetic flux per pole is dependent on the field current, and normally the flux is given by some kind of constant times IF, where IF is the field current. So I better write this down, right? IF is the field current. Now, let's take a look how the circuit is connected. In a normal DC motor, you have two sets of winding. One is so-called uh, field winding. Field winding is the winding for making up the polar flux, uh, polar flux in the stator. So I will label this as RF, which stands for the winding resistance. And you also has uh, a uh, armature resistance. So armature resistance, and the armature is going to be associated with uh, an armature voltage because it is inductive, right? You will end up with a back EMF, right? When the motor is operating, then the equivalent circuit for the armature is given by this one. So in other words, this one is so-called a rotor, uh, and this one is so-called stator, right? Uh, and in a shunt connected motor, they are connected in parallel. They're connected in parallel. Okay, so this is the characteristic of the shunt motor. Uh, and this is armature, and this is the field, right? Uh, so I better highlight it, right? So this is the armature, and this is the field. Field winding. Now, in a circuit like this, um, you have a two parallel path. One is through the field winding, the other is through the armature, uh, and they are connected in parallel. So the total current here is IT. Yeah, IT stands for the total current, and the voltage here, if you agree, right, then the voltage here is going to be VT, uh, uh, and then suppose there is a current here, and the current here is IA, which is the armature current. Yeah, I better remove those red highlight. And we also have a field winding. The field winding uh, also consume current, and the current in the field winding is IF. Uh, now, with all these tips, can we not work out the relations between the torque and also the rotor speed? So the very first thing is to write down the basic formula, the basic relations for the armature. And then IA times RA, where IA times RA is the potential difference across the armature resistance. Right now, we have this formula here. I say, for example, well, this is so-called equation 1, and this is equation 2. So from 1, EA is equals to VP divided by 2 pi A, and then 5. Uh, but hang on a minute, right? This one is a constant. So what we can do is we elaborate a little bit more, right? Phi itself is a column, is a polar flux according to the field column, right? So I substitute these two here, and then omega, right? So I'm now rewrite the formula here. So hang on a minute, right? dp2 pi a and then m. All these are constant. So ideally, you can also express the armature voltage in terms of a lump constant. And this constant is equal to Zp2 pi Zpm divided by 2 pi a. So this is a very important formula that we can play with. And another important formula is here. And we have already got this formula, and we have got EA here. But what we have not played with, what we have not derived is this current, IA. Now take a look in the power. In a normal circumstances, there wouldn't be any significant power to be raised in the field winding. Instead, most of the power will be turned into motion. So suppose your motor torque, uh, let T be the torque, the low torque. Uh, suppose the motor torque is T, and then right, the power itself is going to be T omega, which is the mechanical power. So under an ideal conditions, there wouldn't be too much power loss in the form of friction, heat, or whatever. So the mechanical power will be more or less equals to the electric power input. The electrical power input will be EA, which is the armature voltage times IA. So this is the condition of the motor. Now, if we rearrange this equation, then we will get IA, which is the armature current, equals to T omega divided by EA. Yeah, but hang on a minute. T omega EA, yeah? But haven't I already derived EA here? Yeah, we have already spent a lot of time to derive EA here. So now we substitute all the formula for EA into this one. And note, this is very important. The IA, which stand for the armature current, is now independent of the speed. Instead, it is dependent on the field current and torque. So this is very important relations. The armature current is dependent in the shunt-connected motor. The armature current is not dependent on the speed. So now, can we just substitute EA and IA back to this equation? So now, let's play with this, right? Substitute EA, which is the armature voltage, and IA. back to equation 2. And let's see what happened. Yeah, TA, IA, yeah. So let's do over. Let's check, have a look. EA is going to be KIF omega, right? And then IA times A, uh, so times RA. And then IA, right, is just like this. So this is a very important relationship. Now let's do some rearrangement. Now if you move, uh, let's see, if you move omega, if we do some rearrangement, omega is going to be minus t whatever, yeah. Uh, yeah, it's okay. And then RA, and then KIF square. So this is the first term, and the second term is VT. VT divided by uh, KIF. So eventually, right, we found the linear equations, linear correlations between omega and the low tot. So this is the main characteristic of the shunt connected motor. And according to here, the relations, the correlation between the speed and the torque is going to be, yeah, right now I don't have enough space here. So what I can do is to erase this diagram. We don't need this, right? Yeah, we just continue to play with this. And we plot the speed against, we plot the speed, the motor rotational speed as a function of the torque. And let's see what happened. Now, the slope of the graph is going to be RA divided by KIF square. And the y-intercept of this graph is VT divided by IA. So now VT, which is the supply voltage, divided by KIF. IF is the field current. And the slope is going to be negative. And then the slope is RA divided by KIF square. And it is negative. So from here, we can at least draw a few conclusions. Because of the limit of the slope here, the slope is not going to be infinitive because you always have the field current. The field current is not going to be zero. So the range of speed variation is going to be small. So let's write down the conclusion here. the range of speed variation is limited. So this is a very important conclusion of the shunt-connected motor. The speed is not going to have a very wide range. And also the speed is usually high, right? The speed is usually high, right? And I can write down here. The rotor speed is normally high. So according to this the formula here, if the speed is high, then there has to be some compensation. Uh, the starting torque has to be low. Okay. So you can see it from here, even if the speed is very low, then there's still a lot of, the torque is still very small. So this is the basic, very basic conclusion of the motor. The basic characteristic of the shunt-connected motor. So if you have any questions, please feel free to leave your questions in the comments box underneath the video. Thank you very, very much for your support. Thank you.